In the intellectual landscape of post-war theoretical physics, a period of both profound discovery and deep conceptual crisis, the strong nuclear force presented a formidable enigma, the flood of new unstable particles emerging from cosmic ray observations and early accelerator experiments defied the elegant, perturbative methods that had proven so successful in quantum electrodynamics. The particle zoo, as it would come to be called, was a chaotic collection of entities lacking a clear organizing principle. Physicists struggled with a theoretical apparatus that seemed wholly inadequate for the task. The dominant approach to understanding particle interactions, quantum field theory, appeared to break down when applied to the fierce, short-range couplings that bind atomic nuclei. Within this challenging milieu, in the relative academic quiet of Turin, a young doctoral student named Tullio Regge embarked upon a line of inquiry that would, after a period of prolonged obscurity, fundamentally reshape the study of high-energy interactions. The year 1951 represents the conceptual crucible for his work on potential scattering, an investigation seemingly confined to a classic problem in non-relativistic quantum mechanics, yet containing a mathematical seed of extraordinary power and generality. His dissertation, and the subsequent 1952 paper in Il Nuovo Cemento, articulated an idea so novel and so abstract that its true implications would take nearly a decade to be fully appreciated, ultimately providing a framework that a generation of physicists would use to navigate the complexities of the strong interaction. To comprehend the sheer novelty of Regge's contribution, one must first appreciate the established orthodoxy of scattering theory he inherited. The prevailing method for analyzing the scattering of a particle from a spherically symmetric potential was the partial wave expansion. This technique decomposed the complex outgoing scattered wave into an infinite series of simpler components, each corresponding to a definite integer value of the orbital angular momentum quantum number, represented by the letter L. The scattering amplitude, a quantity whose modulus squared gives the probability of a scattering event, was expressed as a summation over all these integer angular momentum states, from L equals 0 to infinity. Each term, in the sum, was weighted by a factor related to the phase shift, a measure of how much the potential distorted the wave for that specific angular momentum. This method was remarkably effective for low-energy scattering, where the interaction is dominated by a small number of partial waves, typically those with low L values. The series would converge rapidly, and a precise calculation was feasible. However, at high energies, the incident particle penetrates deeper into the potential, and a vast, potentially infinite, number of partial waves contribute significantly to the scattering. The partial wave sum becomes a cumbersome, computationally intractable tool, offering little intuitive insight into the underlying physics. It provided a list of components, with little sense of their collective behavior or any deeper relationship among them. Concurrently, Werner Heisenberg and John Archibald Wheeler had promoted the concept of the matrix, or scattering matrix. This was a more abstract theoretical construct designed to connect the initial state of non-interacting particles long before collision to the final state of non-interacting particles long after. This matrix program aimed to bypass the messy, unobservable details of the interaction itself, focusing solely on the observable outcomes. While philosophically attractive, it initially lacked a dynamic principle to determine this matrix structure, leaving physicists with a sophisticated container but little to put inside it. The world of strong interactions remained a wilderness of disparate phenomena, awaiting a mapmaker. Into this context, Regge introduced a gesture of profound mathematical imagination. Essential insight, developed during the period around 1951, was to question the foundational assumption of the partial wave method that the angular momentum quantum number L must be a physical, non-negative integer. He proposed to treat L as a continuous, complex variable. This maneuver, a process known as analytic continuation, transformed the entire problem. The scattering amplitude, previously an infinite sum over discrete integers, could be reformulated using a powerful technique from complex analysis known as the Watson-Sommerfeld transformation. This mathematical alchemy converts the sum into a contour integral in the complex angular momentum plane. The integral is evaluated along a path that encloses the positive real axis, where the integer values of L reside. By Cauchy's residue theorem, the value of this integral is determined by the singularities of the integrand enclosed by the contour. The crucial physical insight was that the analytic properties of the partial wave amplitude, when viewed as a function of complex L, contained the most essential information about the interaction. Specifically, the poles of this function, points in the complex L plane where the amplitude becomes infinite, dictate the behavior of the scattering process. These singularities were christened Regge poles. This reframing provided a breathtakingly new perspective on known physical phenomena. A bound state, such as the deuteron, which in the standard picture is a stable system with a specific integer angular momentum, in Regge's formalism corresponds to a pole located at that integer value on the positive real axis of the complex L plane. The energy of the bound state is the energy at which the pole appears at that specific integer L. Even more powerfully, the idea illuminated the nature of resonances. Resonances are short-lived, unstable particles that appear as sharp peaks in scattering cross-sections at specific energies. In Regge's framework, a resonance corresponds to a pole that has moved off the real axis and acquired a small positive imaginary part. The real part of the pole's position corresponds to the spin of the resonance, and its imaginary part is inversely proportional to its lifetime, a direct mathematical encoding of the particle's instability. The entire discrete taxonomy of stable particles and transient resonances was thus unified within a single, coherent mathematical structure, the properties emerging from the topography of a single function in the complex plane. The discrete and seemingly disconnected phenomena of bound states and resonances were revealed as two facets of the same underlying analytic structure, distinguished merely by the location of a pole. The concept was made still more dynamic and powerful with the introduction of what became known as a Regge trajectory. Regge demonstrated that the position of a pole in the complex L plane is a function of energy. As one varies the energy of the system, specifically the square of the center of mass energy, denoted S, the pole moves, tracing out a path. This path is the Regge trajectory. Mathematically described as a function alpha of S, the single trajectory could now connect different physical states. For a given trajectory, when its value alpha of S passes through a non-negative integer for a certain negative energy S, it describes a bound state with that spin. As the energy S increases into the positive, physical scattering region, the trajectory moves into the upper half of the complex L plane. When its real part passes through an integer, it produces a resonance of that spin. This meant that a family of particles with different masses and different spins could all belong to the same dynamical family, lying on a single, smoothly varying trajectory. A particle with spin 0, another with spin 2, and another with spin 4 could be viewed as rotational excitations of the same fundamental entity. This was a principle of order of the highest magnitude, suggesting a deep, previously unimagined connection between particles in the chaotic hadron zoo. It was a periodic table for elementary particles, with the Regge trajectory serving as the organizing principle. Despite its intellectual elegance and explanatory power, the initial reception of Regge's work can be described with a certain academic irony as profoundly silent. Published in a respected Italian journal, it remained almost entirely unknown to the main centers of theoretical physics, particularly those in the United States where much of the experimental work on strong interactions was taking place. The paper was a sophisticated mathematical argument about potential scattering, a problem that seemed distant from the urgent relativistic chaos of pure nucleon interactions. For nearly a decade, Regge's discovery remained a curiosity of mathematical physics, a beautiful solution to a problem few were actively considering. The turning point came around 1959. At the University of California, Berkeley, a group of theorists led by the influential Jeffrey Chew was independently grappling with the very same problems of the strong interactions matrix. Their approach, known as the bootstrap program, hypothesized that all strongly interacting particles were composites of one another, the properties determined by a web of self-consistency conditions. While pursuing this program, Chew and his collaborators, notably Stanley Mandelstam, uncovered Regge's papers. They immediately recognized the immense significance of his method. The analytic continuation and angular momentum was precisely the tool they needed to make sense of high-energy scattering behavior and to give substance to their bootstrap philosophy. The transatlantic rediscovery of Regge's work ignited a frenzy of theoretical activity. The Berkeley School, with missionary zeal, took Regge's ideas, which were originally formulated in the safe, non-relativistic harbour of potential scattering, and boldly applied them to the turbulent, relativistic domain of elementary particle physics. The results were spectacular. In 1961, Chew and physicist Stephen Forsythe made a plot of the known strongly interacting particles, the baryons and mesons. They plotted the spin of the particles versus their mass squared. They discovered, to their astonishment, that the particles fell onto remarkably straight, parallel lines. These were experimental Regge trajectories. It appeared that nature, at the subatomic level, was abiding by the very organizational principle Regge had uncovered in his abstract analysis. This finding transformed Regge's formalism from a mathematical curiosity into the dominant phenomenological framework of high-energy physics for the entire decade of the 1960s. Regge theory, as it became known, provided a powerful language for describing high-energy collisions. The scattering of two particles was envisioned as proceeding through the exchange of a virtual particle, but in this new picture, what was exchanged was an entire Regge trajectory. The high-energy behavior of the scattering amplitude was determined by the leading Regge trajectory, that could be exchanged, the one with the largest value of its real part. This led to the postulation of the Pomeran trajectory, named after the Soviet physicist Isaac Pomeranchuk, to explain the puzzling experimental observation that total cross-sections for many hydraulic processes appear to approach a constant value at very high energies. Regge theory offered a rich phenomenology of poles and cuts in the complex angular momentum plane, providing a successful description of a wide range of high-energy scattering data. The reign of Regge theory as a candidate for a fundamental theory of the strong interaction was, however, destined to be finite. The early 1970s saw the rise of a new and ultimately more fundamental theory, quantum cryptodynamics, or QCD. QCD described hadrons as composite particles made of quarks, with their interactions mediated by gluons. This theory, rooted in the principles of local gauge invariance, provided a true microscopic, first principles description of the strong force. From the perspective of QCD, Regge theory was a phenomenological model, an effective theory that brilliantly captured certain emergent, larger-scale features of the extraordinarily complex, non-perturbative dynamics of quarks and gluons confined within hadrons. It was a model of the consequences of the force, a theory of the symptoms, yet its core insights have endured and have been integrated into our modern understanding. The concept of Regge trajectories finds a natural home in QCD. The linear trajectories that Chu and Schwarzschild plotted are now understood as arising from the string-like tube of color flux that forms between a quark and an antiquark. As this system rotates faster, the string stretches, and its energy and angular momentum increase in a way that produces precisely the linear relationship observed. Furthermore, Regge's intellectual legacy was a crucial stepping stone to one of the most ambitious ideas in modern physics. In 1968, Gabriel Veneziano, seeking a mathematical function that satisfied the principles of Regge theory and another concept called duality, wrote down an amplitude that was later recognized as the scattering amplitude for the excitations of an open relativistic string. This marked the birth of string theory, a development that would have been inconceivable without the foundational concept of particles lying on Regge trajectory. In conclusion, Tullio Regge's 1951 work on potential scattering stands as a landmark in the history of theoretical physics, a testament to the power of mathematical abstraction to reveal profound physical truths. Born from a solitary investigation into a classic quantum mechanical problem, his idea of complex angular momentum was an intellectual leap of the first order. It unified disparate phenomena like bound states and resonances, and it introduced the revolutionary concept of the Regge trajectory, a new system of order for the subatomic world. The journey of this idea, from its quiet inception in Italy, through its period of neglect, to its explosive rediscovery and application in America, illustrates the often contingent and unpredictable path of scientific progress. While ultimately supplanted by the more fundamental theory of quantum cryptodynamics, the core insights of Regge's work have become permanently woven into the fabric of physics. They persist as a vital effective theory, as a key conceptual bridge to string theory, and as a beautiful example of how the analytic structure of physical theories can hold the key to their deepest secrets. Regge's genius was to look at a familiar sum over integers and seal a landscape in the complex plane, a vision that provided a map for an entire generation of physicists and forever changed our understanding of the fundamental forces of nature.